Welcome to this video tutorial. We're going to discuss a few reactions. This one is the first one. We have hydrogen and oxygen produced in these bubbles. Now I'm igniting them. And there you go, it was a big bang. Water is produced there, and this is a synthesis equation. Now the next one, we're going to have hydrogen peroxide, that is H2O2, that is now in that big measuring cylinder. I've put a little bit of detergent there just now, mix it up, and here we go. The hydrogen peroxide is breaking down by itself, just very slowly. So it's happening already, this reaction that we're looking at right now. This is actually the opposite from synthesis. This is a decomposition. It's decomposing, it's breaking down. We'll talk about it a little bit more. Whilst we go through it, it would be really good if you have a paper with you, so that you can look at it and write down your notes. The synthesis equation was just very quick just now. Now we have the next equation. So we had we have here potassium iodide, but that's only the catalyst. So the reaction is still hydrogen peroxide. But as we can see in a moment, we're producing a gas. There you go. This gas, as we see, was oxygen, and it's just water. So in this reaction, we had one reactant, but two products, which means it's decomposing, it's breaking down. Next reaction. In this reaction, we have hydrochloric acid. As you can see, I'll put the hydrochloric acid in a petri dish. And the formula for it is HCl. Make a note of this so you can later do the formula and the formula equation. I put some magnesium in there. So this is now hydrochloric acid and magnesium. Doing this reaction, make sure that doing these 4 reactions, make sure that you have the word equation written down so you can later on make a formula for it. So this one, you'll see here now, it again produces a gas, and that's the hydrogen there from hydrochloric acid. Now that's leaving chloric, which is the chloride, which goes to the magnesium chloride, and then the magnesium, which we put in. So the chloric of the chloric acid and the magnesium make the magnesium chloride. Now this is a single displacement, as you've seen that the magnesium displaces the chloride. That's the next reaction. We use lead nitrate. We put a little of liquid in this volumetric flask. It doesn't really need to be a volumetric flask. Just do that for. It's looking good in this flask. So just for show. Again, I remind you, please write down the word equations so that you can then convert them into formulas. Now, after lead nitrate, we now put potassium iodide in it, and you will see here lead nitrate and potassium iodide, and you'll see what happens. Yes, there we see it. Okay, a yellow precipitate, which means insoluble solid, a yellow precipitate is forming as you put in the potassium iodide, and it forms immediately. Just like the one before where we had a single displacement, this is a double displacement, which means that now the lead nitrate and the potassium iodide, they're changing, so it would be then potassium nitrate and lead iodide. Okay, look up the formulas for the last reaction. Now this one is the combustion reaction. We have ethanol here in our flask that we put in this water bottle. Now I'm shaking it. This is now, as you can guess, maybe is just to make fumes, as it has a really low boiling point. So it is actually evaporating at room temperature, but just to help that out a little bit and make it quicker, I shake it, and it's evaporating more. Now we really don't need the liquid ethanol. We're really looking to have the gas, so that's why we want it to evaporate. So we have this ethanol now. Obviously, in any combustion equation, we always have oxygen, okay? So anything that burns, and we're going to ignite that in a moment, but anything that burns always has oxygen. So the reactants of this are ethanol and oxygen. Now let's see what happens.
Switch on.
You see that there's some sparks in the air. These are time-lapsed. The reaction is quite incredible. You'll see that there's water now left there because there was no ethanol left. This is all water produced, and obviously we know there's carbon dioxide in the combustion equation. So these are our 5 reactions. Hopefully you have written them all down, the word equations. Please now convert them to formula equation, and then try to balance them. If you do not know how to balance them, please check out the previous video section about balancing equation, and that will teach you and give us hints how to balance them. So now we're coming to our second part of our tutorial here, where we are going to balance the symbol equations. Hopefully by now you have converted the word equation to symbol equation. The first one that we looked at was synthesis. So that is the synthesis equation. Now this equation was, or the reactants of this equation was when I produced the hydrogen gas plus the oxygen gas, and I've prepared them in bubbles, just with electrolysis, but that's not so important. We know that these were the reactants in this reaction. Now I ignited them, and then we will see that there was a big bang, and produced was water. So these are now the formulas for each of our reactants and products, which means that we have a symbol equation. Now the thing is, now it's not balanced yet. For balancing, it's very important that you know that there is the law of conservation, which means that there need to be the same amount of atoms on the reactant side than there are on the product side. This means that we can create or destroy any atoms. So here, let's see, we have 2 hydrogen atoms as well as we have 2 oxygen atoms. If we look at this side, we do have 2 hydrogens, but we do not have 2 oxygens. So that means that we need to balance it. We cannot change the subscript because then we would change the chemical. We can only add a coefficient, which is a big number in front. So in this case, we need first of all 2 oxygens to be on this side. So we put a 2 in front of that coefficient. This means now that we have 2 oxygens on this side and we have 2 oxygens on that side. However, this also means that we have 4 hydrogens on the product side now, and we do only have 2 on the reactant side. So we need to do a 2 also in front of the hydrogen gas. And there you go, this equation is balanced. Now the second one that we looked at is the opposite of a synthesis, and that is decomposition. The reason why I'm saying this is opposite is because at the synthesis equation we had 2 reactants forming 1 product. Now we have 1 reactant, which is the hydrogen peroxide, and we are forming 2 products, which in this case is oxygen and water. So now we have our symbol equation for this reaction, however, is again not balanced. So let's go ahead and do this. If we're looking at the hydrogens again first, we have 2 hydrogens on this side, we have 2 hydrogens on this side, so that is balanced. So then we have 2 oxygens on the reactant side, and we have 2 here, but also another 1 in water, which means we have 3 oxygens on the reactant side. Usually that means that we would need to, because the 3 is an odd number on the product side, we need to balance it out to be an even number. To do that, we can just put a 2 in front of water. That means we have 2 molecules of waters now. 2 molecules of water, and we have an even number. So that means that we have 4 oxygens. However, we only have 2 on this side, but we can amend that by putting a 2 in front of the hydrogen peroxide. But also that means that the hydrogen changed. So let's see if there is unbalanced hydrogen. We have 4 on the reactant side, but we also have 4 on the product side. And just to make sure that you do know, this and this number is basically 2 times 2 equals 4, just to make sure that you are aware of that if you have missed that before. That's how we calculate how many atoms there are. So that means now that we have 2 molecules of hydrogen peroxide, 1 molecule of oxygen, and 2 molecules of water in this reaction. Now let's go ahead to our third reaction. This one is a single displacement. Okay, and you will realize in a moment why it is a single displacement. We used for that the hydrochloric acid, HCl, and the magnesium metal. Now, produced was, as we saw clearly, it was bubbling quite viciously, so that we have the hydrogen gas, and we have the magnesium chloride, and that's magnesium Cl2, MgCl2. In the next unit that we're discussing, you will learn why it is magnesium MgCl2 instead of just being MgCl. But hold on to that. When we talk about ionic bonding, this will become more clearer. And for the moment, as we're looking at this, we can see here that magnesium has kicked out the hydrogen and displaced the hydrogen. And so in this case, it's only magnesium that's displacing anything. That means it's a single displacement. Again, this is not balanced, so let's have a look. We know that there's 1 hydrogen here. However, there's 2 hydrogen because it's elemental hydrogen and it's always diatomic, this gas. So that's always coming in H2. We have 2 hydrogen here and only 1 here. So let's put the coefficient in front of hydrochloric acid, sorry. And let's check out chlorine. So chlorine, we have 2 of them. We also have 2 of them on the product side. We have 1 magnesium on the reaction side, and we also have 1 magnesium on the product side. So just putting the 2 in front of the hydrochloric acid is actually balancing the equation. You can probably guess then what comes next. So instead of having a single displacement, we now have a double displacement. The double displacement, as you can probably guess, we now have 2 things that swap. In this case, we have lead nitrate, and this is something that you probably would have needed to look up because we're not there yet. We're going to understand that in the next unit. But lead nitrate is PbNO3 2. So that means that we have NO3 is nitrate, and we have 2 of the nitrates, and that's why there's the brackets here. And we add in potassium iodide. Okay, now that is basically swapping, which means that the potassium is kicking out the lead and goes with the nitrate, and the nitrate is basically kicking out the potassium and stays with the iodide. So that means that the products will be potassium nitrate and lead iodide. Okay. So again, we let's see if everything balanced. We have 1 lead atom here. We have 1 lead atom here. We have 2 nitrate atoms here. We have only 1 nitrate atom here. So that means we need to put a 2 in front. Which means also now we have 2 potassium atoms here, but only 1 here. So we need to put a 2 in front here. If you put a 2 in front of lead potassium iodide, that also means that now iodine, we have 2 iodine atoms, and we need to make sure that there are also on the reaction side, which there are. So that's balanced as it is. Okay. Now the last equation that we looked at is combustion. Combustion is one of those equations that is really basic and a basic equation that you should remember. Now I'm going to leave space for two because we have two different combustion. Now the first one is complete. I'm just going to call that comp, okay? And that's really what we're looking for here, but often we're not sure if it's completely complete. So let's have a little look at the complete combustion. That just means that we have enough oxygen. The oxygen is in excess. We don't need to worry about having too little. So in this case, we have ethanol, which is C2H5OH. And of course we have oxygen, because when you want to burn anything, you need oxygen. And you also should know that when we burn anything is always two products, and that is carbon dioxide and water. And we've seen the water in that big water bottle left behind. This is actually quite incredible in this reaction. And many reactions we don't really realize that there is water, because it's often it's just sort of giving off gas, and we can't really see the water, even though there's probably the water vapors mixed within the carbon dioxide. Okay, so let's have a little look here. We know that we have two carbons here, however we only have one, so the first thing we're going to do is put a 2 in front of the carbon dioxide. And then let's check the hydrogens. We have 5 plus the 1 here, 6. We only have 2, which means we need to put a 3 in front of the water. And if we now look in oxygens, we're looking at this side perhaps first, we have 4, the 2 from here and the 2 from there, so 2 times 2 is 4, plus the 3 oxygens in water, which means 7 in total. Now we have 1 oxygen with the ethanol, so we only have 6 others to make sure that it's on a reactant side. So we can put a 3 on here, and then that means this 6 plus the 1 is 7. So on both sides we have 7. Now if we have the incomplete combustion, that just means we have less oxygen. And if we have less oxygen, we don't have carbon dioxide produced, we actually have carbon monoxide produced. So if we write that down again we have ethanol, we have oxygen, and then we have now carbon monoxide instead, and again we have water. And I'm just doing that to actually show you that we have less oxygen. So if we balance this, you'll see again you need a 2 in front of here, a 3 in front of here, but now we have 2 carbons and 3 carbons, 2 oxygen and 3 oxygen, which makes 5 oxygen. So in total, we have 5 oxygen on this side, which means that we actually only need to balance out 5 on here. So 1 is already within the ethanol, that means we only have 4 left. And that means that we need to put a 2 in front of the oxygen. Now you'll see here that the difference is here that you have 3, where you have a complete combustion, so you have a lot more oxygen, well, 1 more molecule, and you only have 2 for the limited combustion. Oh, sorry, I should have put this here like that. I do apologize. Alright, so this is basically finishing up. Hopefully you enjoyed this tutorial and you could apply your balancing of equations a little bit with looking at different reactions. We are going to talk about some of these ionic bonds that are here in the single displacement, double displacement more in the next unit. So see you then.